So let us derive an expression for restriking voltage transient. So I hope you people remember this is the equivalent circuit for the system which we have considered. We have assumed that a feeder is connected to a bus bar and a circuit breaker is there and a short circuit fault has occurred. Now, as soon as a fault has occurred, what should happen? The circuit breaker contact should open. Okay, so when the circuit breaker contacts open at some current 0 point, arc will extinguish. As soon as circuit breaker contacts open, you know arc will strike bit across the contacts of the circuit breaker. Okay, so as soon as the circuit breaker contacts open and the arc strikes across the contacts at some current 0 of the arc current, arc is extinguished. Okay. So a voltage, as soon as arc is extinguished, a voltage V will be suddenly appear across the capacitor. Okay, in this equivalent circuit you can see. Okay, so as soon as the arc is extinguished at some current 0 across the circuit breaker contacts, voltage V will be suddenly applied across the capacitor. Therefore, whatever voltage that is applied across the capacitor, it will be impressed across the circuit breaker contacts. I mean, that will be available. The voltage across the circuit breaker contacts is nothing but the voltage across the capacitor. So this voltage V is across the circuit breaker contacts. So as soon as arc is extinguished, the voltage that appears across the circuit breaker contacts is nothing but restriking voltage. I hope you remember. Okay, so this V we can call it as restriking voltage. Now, so in this system, fault has occurred, okay, and the circuit breaker contacts have opened, okay. So the current which would flow to the fault is now injected into the capacitor and the inductor. We have assumed that the resistance is negligible in the previous class, okay. I hope you remember the concept which we have discussed already, okay. So the current I would flow to the fault is now injected into capacitor and inductor. Okay, so I is equal to what? IL plus IC. I hope you people have your notes and pen in your hands. Okay, so start writing. The current that is injected, that flows due to the fault, okay, into the capacitor and inductor, I is equal to IL plus IC. So what is IL in terms of voltage? 1 by IL integral V dt, and what is IC? C into dV by dt. You already know that. Okay, so you people already know that. So if you differentiate this I, you will get di by dt is equal to V by L plus C into d square V by dt square. Okay. And let us assume initially at initial time t equal to 0, the current is also 0. Okay. When the means at the instant when the circuit breaker is about to open, we can say at t equal to 0, the current is also 0. Okay. Did you copy down? Did you write down these equations? If you complete type C, someone type C. If you inform me, I will proceed. In the chat box, type C if you complete. No need to write this theory, just write down these equations. Okay, no need to copy also. Why? Because you know all these terms. Okay, they are very much familiar to you. Did you complete? While taking attendance, I am going to check your notes today. All of you, make sure you people are writing. While taking attendance, definitely, I will ask you. You no need to give your attendance. Simply you open your video and show me your notes. Did you complete? Okay. Just type C, that is more than sufficient. Okay. No need to type all the alphabets of complete word. Okay. So now, what is the voltage across the circuit breaker contacts? V. V is nothing but V max cos omega t. Okay, so the value of the current before opening the circuit breaker is I equal to V max by omega L sin omega t. Okay, so if V is V max cos omega t, I will be V max by omega L sin omega t. So differentiate this I by dt. So when you differentiate it, you will get V max by omega L omega cos omega t. Okay, now since at t equal to 0, okay, so initial time means the current before opening the circuit breaker we have assumed. So the current before opening the circuit means the time is what? Time is 0. So magnitude of di by dt is what? You will get V max by L. Okay, substitute t equal to 0 here in this equation. Okay, in this expression. Okay, substitute t equal to 0, you will get magnitude of di by dt as V max by L. So I'm giving some numbering to each and every expression here. Whatever numbering that I'm giving, you people also give the same numbering. Okay, so now this is our equation number 5. Substitute this equation number 5 in equation number 2. What is equation number 2? Di by dt equal to V by L plus C into d square V by dt square. Okay, so instead of di by dt, write down V max by L. So V max by L will be equal to what? V by L plus C into d square V by dt square. So assume it as equation number 6. Okay. Now, voltage that appears across the circuit breaker contacts as soon as the arc is interrupted is nothing but restriking voltage. So V is equal to V max cos omega t, you already know. So write down that. Okay, write down the expression for restriking voltage V equal to V max cos omega t. So did you complete? As soon as you complete, you people inform me. Just type C alphabet, that is more than sufficient as well as you complete. Completed? Okay. Okay, now this is our restriking voltage V equal to V max cos omega t. Okay, now differentiate V by dt. You will get minus V max omega sin omega t. Again differentiate dV by dt. D square V by dt square will be minus V max omega square cos omega t. Okay, so what is the magnitude of this d square V by dt square? That is V max omega square cos omega t. Minus will not be there. Okay, assume it as equation number 7. Okay, now substitute this equation number 7 in equation number 6. What is equation number 6? V max by L equal to V by L plus C into d square V by dt square. Okay, substitute this in that equation. Okay. Okay, so there V max by L equal to V by L plus C into d square V by dt square is there. Instead of d square V by dt square, substitute this expression. Okay, you will get V max by L equal to V by L plus C into this V max omega square cos omega t. You will get, assume it as equation number 8. Okay, so you have got some expression here. V max by L equal to V by L plus C V max omega square cos omega t. Now, you know the expression for the natural frequency f is equal to 1 by 2 pi root 1 by LC or 1 by root LC. Okay, so from this expression you just rearrange the terms. I have sent this 2 pi to the left side of this expression. I have got 2 pi f equal to 1 by root LC. So what is 2 pi f? 2 pi f is nothing but omega. Okay, 2 pi f is nothing but omega. So omega equal to 1 by root LC. Assume it as equation number 9. Okay, and if omega is equal to omega equal to root of 1 by LC or equal to 1 by root LC, what is omega square? Omega square equal to 1 by LC. Now substitute this equation omega equal to 1 by root LC. Okay, omega equal to 1 by root LC and omega square equal to 1 by LC in equation number 8. Okay, so you have omega here and omega square is there. So did you complete this? Did you complete this slide? Very good. Okay, so omega equal to 1 by root LC. So omega square is equal to what? 1 by LC. Okay, so substitute equation 9, that is omega equal to 1 by root LC, and equation number 10, that is omega square equal to 1 by LC in equation number 8. Okay. So what is our equation number 8? 8 is V max by L equal to V by L plus C V max omega square cos omega t. So wherever omega and omega square is there in equation number 8, substitute this omega and omega square values. So instead of omega square, I have written here 1 by LC here. You can see this is my equation number 8, which has been modified. So omega, instead of omega, I have written 1 by LC, and instead of omega square I have written 1 by LC, instead of omega I have written 1 by root LC. Okay, so we have substituted 9 and 10 in 8. Okay, so I have solved each and every step here. So if you follow my notes, that is more than sufficient for you to learn this. Okay, in the textbooks they won't derive, complete derivation will not be there. Okay, so okay, so this is what we have got, and you can see here there is 1 by LC, and here in the denominator C is there and the numerator C is there. Just cancel these two, C's will be cancelled, and what is left over is V max by L equal to V by L plus V max by L cos V max by L cos 1 by root LC t. Okay. So you can take L common here, okay, in the right hand side and on the left hand side. You can take L common, L will be cancelled. Left over is V max equal to V plus V max cos 1 by root LCT, okay. And you can see V max on the left side and on the right side, V max cos 1 by root LCT is there. You can send V max terms on one side. So you will get V equal to V max minus V max cos 1 by root LCT. Okay, and you can take Vmax common, you will get V equal to Vmax 1 minus cos t by root LC. What is small v? What is small v? It is nothing but our restriking voltage. So you have got an expression for restriking voltage. So this expression is the standard solution. It is a solution for the standard equation Vmax by L equal to V by L plus C into d square V by dt square. So this is the expression for restriking voltage. So expression for we are going to solve some problems. In the problems they will ask to determine the restriking voltage. Okay, so for the given data whatever they give. Okay, so you must know these expressions. Okay, so what is the formula for restriking voltage? That is V equal to V max into 1 minus cos t by root LC. Did you complete this slide? Okay then. So this is we have got an expression for restriking voltage. So before going to derive a few more expressions for some other terms, okay. So let us see the classification of restriking transients. So the restriking transients can be classified as single frequency oscillatory transients and double frequency transients. Okay. So let us see this single frequency oscillatory transients. So same circuit, the equivalent circuit for single frequency transient is this one, the same circuit which we have already utilized. to derive the restriking voltage expression. Okay, so same if you remember the restriking voltage, restriking phenomenon, okay, in the of the last class, same whatever theory I have explained, same theory I'm going to explain now also. Okay, so this is the equivalent circuit for your single frequency oscillatory circuit. Okay, so you know the natural frequency of oscillation is given by f is equal to 1 by 2 pi root 1 by LC. Of course, frequency is measured in hertz. Okay, so the frequencies which are induced when the circuit becomes oscillatory, those frequency can be within the range of 10 hertz to 10 kilohertz depending on the L and C. You know, when at what condition the circuit becomes oscillatory, I have already explained in the last class. Okay, so this circuit configuration will be complex because we know in the power system the capacitors and inductors are distributive in nature, and the circuit of the power system is complex. The restriking voltage transient for these complex circuits can have several component frequencies ranging from few hertz to several kilohertz. Okay. Usually these transients will occur while opening a terminal fault. Okay. So, and in such cases, the reactance between the fault and the circuit breaker will be negligible. Okay. So, the reactance between the fault and circuit breaker will be negligible, and usually single frequency oscillatory transients will occur if whenever fault occurs at the terminal of the system. Okay. So, this is about single frequency, and the voltage waveforms whenever single frequency transients occur. So this voltage waveform we have already seen it. Okay, you know all these terms. Okay, so I have already explained about that. Okay, next one is double frequency transient. So for the double frequency transient to occur in the system, okay, if L and C are on both sides of the circuit breaker, in such circuits, okay, double frequency transients will occur. Okay, so if fault occurs in such system in which the circuit breaker is in between L and C on both sides, then you can see the terminal, you assume this node or the terminal as one of this circuit breaker. On the other side, assume this terminal as two. Okay, so before clearing the fault, okay, as if fault occurs in such system in which circuit breaker is placed in between L and C on both sides, then if fault occurs in such system, before clearing the fault, both terminals 1 and 2 are at same potential. Okay, both terminals will be at the same potential. After clearing the fault, okay, before clearing the fault, 1 and 2 terminals will be at the same potential. After clearing the fault, the arc has been extinguished. Okay, as soon as fault is clear, arc has been extinguished. Both the circuits will oscillate, both the circuits, LC circuit, L1, C1, L2, C2. Both the circuits will oscillate at their own natural frequencies, and a composite double frequency transient will appear across the circuit breaker poles. Okay, at these poles, pole number 1 and pole number 2, what will happen? A double frequency transient will appear. Okay, so the double frequency transient will look like this. Okay, so this is the fault current, and this V is the system voltage. Okay, at some current 0. Okay, suddenly when arc is interrupted, arc is extinguished, double frequency transients will occur because of the presence of L and C on both sides of the circuit breaker. Okay, so this is about the double frequency transients. Okay, so let us see the characteristics of the restriking voltage. Okay, so the characteristics of the restriking voltage which will affect the performance of the circuit breaker are two characteristics. One is the amplitude factor, next one is the rate of rise of restriking voltage. Okay, so let us see what is this amplitude factor. So amplitude factor is the ratio of peak of the transient voltage by peak system frequency voltage. Okay, so it is the ratio of peak of the transient voltage. So if you see here, just now you have seen this waveform. double frequency, forget about double. Okay, let us go to the single frequency oscillatory transient. So you can see here, because why I'm going to single frequency, why? Because in the double frequency, two peaks will be there. In order to explain the concept, I'm taking the single frequency transient. Okay. So you can see that this is the peak of the transient voltage, isn't it? Okay, this is the peak of the transient. So amplitude factor is the ratio of peak of the transient voltage by peak of the system frequency voltage. What is the system frequency voltage? You can see here, this is the system voltage. Okay, so sinusoidal waveform, this is the system. So what is its peak? This is the peak value. Okay, this is the peak of the system voltage. So amplitude factor is the peak of the transient voltage by the peak of the system voltage. Okay, so peaks, system frequency, even if that word system frequency means normal frequency, you should not confuse. Okay, and this is about the amplitude factor, which is the ratio of peak of the transient voltage and peak of the normal frequency voltage, in my words. Okay, so next one is rate of rise of restriking voltage. So rate of rise of restriking voltage is the slope of the steepest tangent to the restriking voltage curve. Okay, so if I am able to draw the slope, okay, slope, as soon as this transient occurs, if I am able to draw a slope to this transient, okay, so the steepest tangent that I get, okay, so the steepest tangent slope is nothing but the rate of rise of restriking voltage. It can be as steep, you can see it's slightly bent. Okay, so if I draw one more line here, straight line, so that line represents it is more steeper. Okay, so see, this is the most steepest slope. If I draw a straight line with respect to this waveform, peak of this restriking voltage. Okay, this way you can see, it's a straight line. I can draw a line parallel to this. That will be the slope of this restriking voltage. Okay, so it is a straight line. It can even be a curvy in nature. Okay, it can be a curvy in nature with, as you can see here, it is slightly bent and transients are occurring. Okay, so this line is the slope for this transient, and if I draw a line, straight line here, this dotted line, if I extend, that is the slope of this transient. Okay, so rate of rise of restriking voltage is the slope of the steepest tangent to the restriking voltage curve. It is expressed in kilovolt per microsecond. Okay, and rate of rise of restriking voltage will be always proportional to the natural frequency. Okay, rate of rise of restriking voltage will be always proportional to the natural frequency. Okay, so for a restriking voltage having a single frequency transient component, okay, so this one, okay, for a restriking voltage having single frequency transient component, the rate of rise of restriking voltage is obtained by dividing the maximum amplitude of the oscillation by the duration of the first half wave. Okay, so if I want to determine the rate of rise of restriking voltage for a single frequency transient component, this is a single frequency transient component, isn't it? Okay, so if I want to determine rate of rise of restriking voltage, I can determine it by dividing the maximum amplitude of the oscillation. Maximum amplitude of oscillation is this peak value. This value is the maximum. Okay, that is 2V max. Okay, that is nothing but 2V max by the duration for the first half wave. Okay, so how much time it is taken for first half wave? Okay, so first half wave, for first half wave, how much time it is taken? Okay, will give me the rate of rise of restriking voltage. Of course, we are going to derive an expression for rate of rise of restriking voltage. Don't worry. Even if you are unable to calculate in your mind, frame any expression in your mind, don't worry. Okay, so higher values of natural frequencies can be related with higher rate of rise of restriking voltage. Okay, the duty of circuit breaker is much more severe when employed in a network of higher natural frequencies than on a network of low natural frequencies. Okay, so the circuit breaker means its duty becomes more severe whenever it is employed in a network for higher natural frequencies than on a network of low natural frequencies. This is because the average rate of rise of restriking voltage is much greater in the former case. Okay, so former case means the circuit which is employed in means the circuit breaker which is employed in a network of higher natural frequency, means the network which is operating at higher natural frequency. In such circuits, average rate of rise of restriking voltage is very much greater when compared to average rate of rise of restriking voltage in a network of low natural frequencies. Okay, so if the circuits whose average which operate at low natural frequencies, the voltage across the circuit breaker contacts will rise slowly in such circuits, thereby giving longer time for building up of the dielectric strength. Okay, did anybody mess with my presentation? Are you able to see the screen?
No, ma'am.
Somebody, something, so I just read some message. Somebody has started presenting. Already I am presenting this screen.
By mistake, she presented, ma'am.
By mistake, but what happened is you people lost the screen. That's the matter. Okay. So what happened? Screen is not visible. Resume your presentation. Okay. Okay. I'm presenting. I have pinned it. Is my screen visible to you? It is not visible to me. Can anybody respond?
No, ma'am.
So, okay. I will stop presenting and once again I will present. Okay, now it is visible. Okay. Okay, so the circuits which operate at low natural frequencies, in such circuits, if fault occurs, then the voltage across the circuit breaker contacts will rise slowly, thereby giving longer time for building up of the dielectric strength. Okay, so this is about rate of rise of restriking voltage and amplitude factor. So let us derive an expression for rate of rise of restriking voltage. Okay, so just now we have derived an expression for restriking voltage. V is equal to V max 1 minus cos T by root LC. Okay, so rate of rise of restriking voltage. Rate of rise of restriking voltage means what? D by dt of V. Okay, rate of rise of restriking voltage means d by dt of V. So d by dt of V, what is V? V max into 1 minus cos T by root LC. So V max 1 minus cos T by root LC. So just differentiate it with respect to time. You will get rate of rise of restriking voltage as V max by root LC sine T by root LC. As soon as you complete, you just inform me. So rate of rise of restriking voltage is nothing but if V is the restriking voltage, rate of rise of restriking voltage is d by dt of V. So differentiate V with respect to T, you will get an expression triple RV is equal to V max by root LC sine T by root LC. If you complete, just type C. Did you complete? Okay then. Okay, you have got an expression for rate of rise of restriking voltage. Now, let us see the maximum value of restriking voltage. Okay, you already know the expression for restriking voltage. Let us see the maximum value. Okay, so restriking voltage will be maximum whenever restriking voltage is what it is V. Okay, so you already know the condition for maximum. Okay, so for any term, if you want to determine the maximum value, what is the condition you already know. So what is it? So if I want to determine the maximum value of so and so term, I must differentiate it with respect to time and equate it to 0 and assume t equal to t max. Okay. So dv by dt equal to 0 and t equal to t max. So dv by dt you have already got determined this in the previous slide. Okay. For rate of rise of it is nothing but rate of rise of restriking voltage. Okay. So substitute dv by dt and equate it to 0 instead of t, write t max. Okay, and just simplify it. V max by root LC sin T max by root LC is equal to 0. So this whole term will go to the right side, it becomes 0. You will get sin T max by root LC. Okay, so send sin to the other side. So T max by root LC sin inverse of 0. Sin inverse of 0 is pi. So T max by root LC is equal to pi. Okay, so T max equal to pi into root LC. So T max value is equal to what? Pi into root LC. Did you complete? Type C if you have completed. You didn't complete? Okay then. Next. So T max is equal to pi root LC. Okay. So what is V actually? V equal to V max into 1 minus cos T max by root LC. So write V equal to V max instead of T, write T max. Okay. In the expression of restriking voltage, in the expression of restriking voltage, instead of V, write V max, instead of T, write T max. Okay, this is small v, this is capital V. Just remember that this is the peak value. Okay, this capital V max is peak value. Small v max is maximum value of restriking voltage. Don't confuse. Okay, this is Vm actually. I have written max here. Okay, so what is small v max is equal to capital V max into 1 minus cos T max. What is T max? Pi root LC. Substitute pi root LC, root LC will be cancelled. Cos pi you will get minus 1. So 1 minus of minus 1 you will get 2. So V max equal to 2 V max. Okay, maximum value of restriking voltage is 2 times of the peak value of the voltage. Okay, 2 V max. Okay, maximum value of restriking voltage is 2 V max. This is what we have seen in that waveform, if you remember. If you complete, I will show you the waveform. Now we are about to complete. Okay, we are about to complete. If you complete, just inform. Just type C. So restriking voltage, maximum value of restriking voltage is equal to is 2 times of the peak value of the transient voltage. Completed? Okay then. So Vmax restriking voltage, maximum value of restriking voltage is 2 Vmax. So if you remember the waveform, this waveform, if you remember, see, as soon as circuit breaker contacts are open and as soon as arc is extinguished, the voltage that appears across the circuit breaker contacts, restriking voltage is 2 Vmax. It is the maximum value of the restriking voltage. That is 2 Vmax. Okay. Okay, next, let us see the maximum value of rate of rise of restriking voltage. So rate of rise of restriking voltage is nothing but dV by dt. Okay, so what is the maximum value of rate of rise of restriking voltage? So in order to determine the maximum value, you must differentiate it with respect to t, and we assume t is equal to maximum. So dV by dt, you just differentiate it with respect to t. It will become d square v by dt square and equate it to 0 and assume t equal to t max. Okay, in order to determine the maximum value of rate of rise of restriking voltage. So you already know dV by dt, that is V max by root LC sine T max by root LC. Okay, so determine d square V by dt square equal, you will get V max by root LC into 1 by root LC cos of T max by root LC and equate it to 0. Okay, instead of T, wherever T is there, I have written T max and I have equated to 0 to determine the maximum maximum value. Okay, so here of course I will get the T maximum value here. So this is what I have got, root LC, it will become LC. So V max by LC cos of T max by root LC is equal to 0. You will get this whole term will go to the right side, it will become 0. So you will get cos T max by root LC equal to 0. So T max by root LC is equal to cos inverse of 0. Okay. So cos inverse of 0 is nothing but pi by 2. So T max by root LC is pi by 2. T max is equal to pi by 2 root LC. LC you just root LC, you send it to the right side. Did you complete this slide? You people try to solve on your own, derive on your own. Don't just simply copy. If you copy, it is of no use. Completed? Did anybody complete? Okay then. So T max by root LC cos inverse of 0, that is nothing but pi by 2. So T max is equal to what? Pi by 2 into root LC. So this is the max time at which rate of rise of restriking voltage will be maximum. So what is rate of rise of restriking voltage? Formula you already know, V max by root LC sine T by root LC. Okay, so instead of T you write T max, triple R V max you just write down. So rate of rise of restriking voltage max is equal to V max by root LC sine T max by root LC. So whatever you have got T max value, you just substitute here in this formula. Pi by 2 root LC will be cancelled, sine pi by 2 will be left over. So sine pi by 2 is 1, so you will get V max by root LC. So maximum value of rate of rise of restriking voltage is V max by root LC. Maximum value of rate of rise of restriking voltage. is Vmax by root LC. Did you if you complete type C, inform as soon as you complete. Did you complete? Did I miss? If you have completed type I was disconnected because of power discontinuity. It's okay. I will start presenting using my mobile. Wait, first I have to download. I'm going to share the screen using my mobile. As soon as you see the screen, you just inform me. Are you able to see the screen? Can anybody unmute and inform me? Yes, okay then. So this is the expression for rate of rise of restriking voltage that is equal to maximum value of rate of rise of restriking voltage that is equal to Vmax by root LC. Okay. So you already know the formula for natural frequency. That is 1 by 2 pi root 1 by LC. So I can rearrange the terms here. I have sent this. Take a pen. Okay, I can send this 1 by root LC to the left side. I can send this Fn to the, I'm sorry, I can send this 1 by root LC to the left side. I can send this Fn to the right side. So I will get root LC is equal to, root is equal to 1 by 2 pi Fn. Okay, so I have got an expression for root LC. I can substitute the root LC in the above expression. Okay, in the what is maximum value of rate of rise of restriking voltage, it is Vmax by root LC. So instead of root LC, write 1 by 2 pi Fn. Okay, or in this expression also I can rearrange the terms. I have written here root LC is equal to Vmax by triple max. Okay, so and later on I have equated, so you can do anything. So at last I will get Vmax is equal to 2 pi Fn Vmax. Okay, you can derive the expression in terms of natural frequency for the maximum value of rate of restriking voltage in terms of natural frequency. Okay, so maximum value of rate of restriking voltage is 2 pi Fn Vmax, capital Vmax. If you complete this slide, somebody unmute and inform me. We are about to finish the class. Did you complete? You people unmute and inform me. Am I in the class?
Yes, ma'am.
Complete. Okay. Did you complete? Did you complete?
No, ma'am. Writing, ma'am.
You are still writing? Okay, then write. Complete it. Did you complete?
Yes, ma'am.
Average value of rate of rise of restriking voltage. Completed? Okay, very good. Next is expression for average value of rate of rise of restriking voltage. So if I want to determine the average value of rate of rise of restriking voltage, okay, so it is usually determined up to the first peak of the oscillation, the transient which appears. So just now power has been reconnected. Okay. Okay then. So average value of rate of rise of restriking voltage up to first peak of oscillation is equal to maximum restriking voltage by time up to first peak. Okay, so what is the maximum value of restriking voltage? We have already derived that expression. Maximum value of restriking voltage is given by 2V max, if you remember. And time up to first peak is T equal to pi root LC. Okay, time up to first peak is T equal to pi root LC. That also we have already derived for the restriking voltage. Okay, so average value is 2V max by pi root LC. Okay, so usually problems will be given in the exam to determine the average value of rate of rise of restriking voltage. And to determine rate of rise of restriking voltage. Okay, so whatever derivations that we have done today, they are very important. Generally, problems will be asked on this. You complete this slide. After that, I will take attendance. Okay, so power has been reconnected. So within 2 minutes, I will join the class using my desktop. Meanwhile, you will complete this slide. We were about to complete the class and suddenly we lost power.